Welcome everybody to chapter 11. Have you ever heard of chapter 11 outside of a math class? I've never heard it in the real world. Chapter 11 is a euphemism for people who file for bankruptcy. Yeah, it's because of the government code on filing for bankruptcy. They call it chapter 11. I'm filing for chapter 11. That means I'm filing for bankruptcy. Are we filing for bankruptcy today? No, we're just moving on to the next chapter in the sequence, which is chapter 11. Okay. Now, in this section, we're going to be looking at radical functions. Okay, radical functions, and we're going to start by looking at inverse functions of quadratic and cubics. Okay, because we're really interested in not the quadratic and not the cubic. We've already studied those. We're interested in their inverses. Okay. Now, to look at the inverses real quickly. Y'all know about inverse operations, right? Inverse operations. What would be the inverse operation of multiplication? A division, right? Because division undoes multiplication. What would be the inverse operation of subtraction? Addition. They undo each other. So that's what an inverse does. It undoes the previous function. We're going to look at functions, not just operations. But that's what an inverse function does. It undoes the work of the other function. So let me ask you this question. Let's say I have a function f of x. Let's just call it y. I want you to give me a number y that is going to be the following, okay? You think of a number in your head. You think of a number in your head. Got a number in your head? Okay, I'm going to call the number in your head x. I'm going to call the number in your head x. I want you to double that number, multiply it by 2, and then I want you to add 3 to it. Okay? You got your new number? Okay, what did we do to get our new number? We multiplied by 2, and we subtracted 3, or added 3, sorry, oops. What if I wanted you now to get back to your original number? What would you do with your output y? What would you do first? Would you divide by 2 first? You would have to, good, you would have to subtract 3 first, right? Why would you have to subtract 3 first? Well, there's a couple of reasons. Subtraction undoes addition, right? And also adding 3 was the last thing that you did, wasn't it? So it has to be the first thing that you undo. So now that we've subtracted 3, what would you do to that number to get back to your original? You'd have to divide by 2. And that gets you back to your original x, right? Let's try it. You try it with your number. Keep that number in your head. I'm going to start with 5. I'm going to let you know what my number is. So I started with 5. I'm doubling it to get 10, and then I'm adding 3 to it to get 13. Now I want to get back to my original number, so I'm going to take my 13, subtract 3 to get 10, and then divide by 2 to get 5. Yes, yes? It's a pretty simple thing, right? We do the inverse operation in the reverse order, okay? Here's the only difference with functions. Instead of keeping it as x and y, once we have our new function, we're actually going to, instead of calling this x, and instead of calling this y, we're going to call this y, and we're going to call that x again, but we're going to put a little -1 symbol on that y to show that it's y inverse. That's how I read that. I read that as y inverse. The reason we change it back to x is because when we have functions, we always let x be our input. So the old output, for me, the old output of 13 is now my new input of 13. And I get back to where I started, okay? So these right here, this y and this y inverse, they form a pair of functions that undo each other, okay? Has anyone in here ever purchased anything online and you had to give your credit card information or your parents' credit card information? Yeah. You know how that credit card number gets to the purchaser on the other end through cyberspace? You think they just send the numbers directly over? Nope. It's always encrypted, right? You have to go to secure websites or use a secure server like PayPal. What they do is they code your message because there's people out there, there's dishonest people. I hate to break this to you, but there are dishonest people out there that would love to intercept your credit card information so they can use it for themselves to buy more math supplies for their own math parties. Okay? So your credit card information is always coded. Well, guess what? They code it with a certain function like 2x plus 3, and then when it gets to the receiver on the other end, they decode it using your inverse. Okay? Now, it's a very complicated way they're coding it. They're not coding it just with this function here. It's a very sophisticated method called public key encryption. But it's the same idea. You're coding a message with 2x plus 3, and then the user on the other end decodes the message with x minus 3 divided by 2. That's the whole idea behind inverse functions. Are you cool with that? Okay. So really, let me show you another way to do it. Here's the other way to do it to algebraically. To find, and I'm deviating from the notes here a little bit, to find an inverse function. Okay. Number one, we're going to switch x and y. Instead of doing it at the end, we're going to do it at the beginning. That is kind of the main important thing behind an inverse function. We're going to switch x and y, and then number two, we resolve for y. And then the last thing we do is we name it y inverse. Okay, that's it. Now let's see if that works for 2x plus 3. Here's an example. Let's start with y equals 2x plus 3. We got the inverse function intuitively. Let's see if we can get it algebraically. What's the first step? Switch x and y. So I get x equals 2y plus 3. Now, how would you solve for y? What would be the first thing you do if you solve for y? Wouldn't you subtract 3 from both sides? Yeah, so we get x minus 3 equals 2y. And then how would you get y by itself if it's currently being multiplied by 2? You would divide both sides by 2, and we get x minus 3 over 2. Isn't that the same thing we got up here intuitively? Yes. So this little formula right here, switch x and y, resolve for y, it takes away all the guesswork. You don't have to try and find the inverse intuitively, okay? It takes all the guesswork out of it. Everyone cool what an inverse function does? It's like coding a message, and the inverse function decodes it. Now, here's the question that I have for you. Is it possible that someone codes a message a certain way, and then there's more than one way to decode it, and the message gets garbled? Could it be that there's more than one way to decode a message? Let's see. What if I coded a message with this function? What if I coded a message with y equals x squared? And by coding a message, what I mean is, let's code a number. What would happen if I plugged in a 5? What would the 5 come out to be? A 25. So what if I code my 5 and I turn it into a 25? How would I get my 25? How would I get my 5 back? What would be the inverse of squaring a number? Square rooting it, right? So I could take the square root of 25 and get what? I get 5. But what if I code a negative 5? What if I plugged a negative 5 into x squared? What do I get? I also get 25. Oh, crap. What if I'm decoding the 25 on the other end, and I don't know if the original number was a 5 or a negative 5? There's no way to know that, is there? I don't know if the person on the other end that sent me the 25 meant to have it as a 5 or meant to have it as a negative 5. So not all functions have an inverse that codes uniquely, which means they're not a function. The inverse itself is not a function. Now with lines, it works perfectly. But when you have quadratic functions, you got to be careful because there's more than one way to decode the message. All right, let's look at these definitions here now to start this section. A function, of course, you know what a function is. That means for each element in the domain x, there's only one corresponding element for y. So basically we have x goes to only one y. That's an easy way to remember it. Each x goes to only one y. All right. So another way to think about this is no repeated x's. No repeated x values. You can't have x going to a 1 and x going to a 2. Okay? That's the vertical line test. The vertical line test is a good test for functions. If the vertical line touches two values at one time, that means that x value went to two different places or more, and that's no good. Okay, so that's a review. Now, this many to one function, I don't really like this terminology, but it's a function where many different x values map to one y value. That's okay. Okay, we have different x's now, different x's to the same y value. What would the graph look like if you have several different x's going to the same y value? Like this x value going to this y value, this x value going to the same y value. Let's call it 1. This x value over here is going to the same y value. What would that look like if you connected the dots? What type of line? What kind of straight line? Horizontal line. Yeah. So it's okay to have repeated y's. Is that still a function? Does it pass the vertical line test? Yes. So repeated y's are okay for a function. They just have to come from different x's, right? Think of the y value as being the cost at a grocery store. The cost comes out to be $100. Are there many different things in the grocery store that you can use to cost $100? Lots of different combinations of items that can add up to $100. So you can have a repeated y value. But what you can't have at the grocery store is you can't take a box of granola bars up to the register and have that thing cost two different prices, right? That would not be a function. That would not work. My granola bars don't cost $5 and $25. Okay? They're only $25. Oh my gosh, granola bars got expensive all of a sudden. This is the one that we're interested in this section right here. A one-to-one function. Okay? It sounds romantic, doesn't it? A one-to-one function. Okay? Here's the definition of a one-to-one function. Each x value maps to only one y value. Now it's incomplete. And each y value, I don't know why it's incomplete, each y value maps, I'm going to use that word maps. That means changes or goes to. That's another word for maps, goes to. Each y value maps to only one x value. It's like a faithfully monogamous relationship. Okay? A faithfully monogamous relationship. Each x is only seeing one y, and each y is only seeing or dating one x. That's one-to-one. We have a one-to-one relationship. These lines over here are one-to-one. If I plugged in a number for x, it's going to come out to be a single number. And if I plug it into the inverse, it's going to come back to only a single number. Those are one-to-one. Is x squared one-to-one? I'll get it. What do you think about x squared? Is x squared one-to-one? Hey, come on in. Thank you. I was keeping your desk warm if you wonder why the desk is warm. Is x squared one-to-one? Each x maps to only one y, correct? Like if I plugged in a 5, where did the 5 go when I squared it? It went to 25, only one value, right? What happens if I plug in a -5? Does it only go to one place? Well, it only goes to one place. It only goes to 25, doesn't it? But, do each of the y values come from only one x? No. The 5 is faithfully dating 25 and only 25. The -5 is faithfully dating 25 and only 25. But what is 25 doing behind their back? Dating both of them. That is not romantically faithfully one-to-one. That's two-timing. That's two-timing. X squared is two-timing every single x value except 0. Two-timing every single value. So that's what a one-to-one function means. Now, how can you tell that a one-to-one function is one-to-one if you have the graph? Easily, right here. A one-to-one function passes both vertical and horizontal line tests. Okay? There's no repeated x's, nor y's. Does the graph of x squared pass a horizontal line test? If you think of a smile, no, it fails the horizontal line test. It touches the graph twice everywhere, except at the origin, at the vertex. So you can't have repeated x's or y's. Now, here's why we want one-to-one functions. This is why one-to-one functions are important. Think of coding messages again. A one-to-one function means that there's only one way to code the message, And then in return, there's also only one way to what? Decode the message. That's why one-to-one functions are especially important when we're talking about inverses. Now, there is hope. Here's what's hopeful about it. There is hope. For functions that are not born to be one-to-one, like the graph of x squared, we know the graph of x squared looks like this. It fails the horizontal line test, right? So it's not one-to-one. There is hope for functions, though, that aren't one-to-one. If you limit their domain, if I looked at the graph of x squared and I said to everybody, hey, we're only using values of x that are either 0 or positive, we're only using that piece of the graph. Would that green piece of the graph by itself pass the horizontal line test? Yes. Now, using -5 is not even an option. So that the person on the other end knows that and says, oh, if they gave me a 25, it had to have come from +5 because they're not allowed to use negatives. That's called restricting the domain. We can always restrict a domain to like surgically correct, if you will, a function that wasn't born one-to-one, that function that failed the horizontal line test. We can fix it. Okay, y'all feeling good about inverse functions? All right, let's look at example 1 then. Finally, we're on example 1. There's kind of laying the foundation. The function f of x, raised, see how it's raised up there? The function f of x is defined by the following ordered pair. So we can define a function several different ways. We can define it by a graph, we can define it by an equation, or we can define it by a set of ordered pairs. Okay? It says to, first of all, let's see if this is a function. How can we tell if this is actually a function? It said it is, so it must be. How can you tell from data that it's a function? We can't look at the vertical line test unless you want to plot them. That's how you would find the inverse. Let's come back up here to the definition of a function. Okay, what did I say is real easy to see if you have a function? No repeated x's. You can't have an x going to two different things. Let's look at this right here. I have a -2, a -1, a 0, a 1, and a 2. Are those all different? Yes, so this is a function. Whoa, writing with the highlighter. I haven't done that in a while, stupid highlighter. Okay, this is a function because there's no repeated x's. So that's what makes it a function. Now, it says to find the inverse by reversing the coordinates. Now, notice what they used here. Instead of y to the negative first, it's f to the negative first. That's how we write f inverse. This is how we read this. We read this as f inverse. We like to reuse the f because it shows that it's related to the original function, but we have to distinguish it somehow, and the -1 means that, hey, I undo what f does. Now, they are each other's inverses, so f also undoes the work of f inverse. Does that make sense? It's like you and your sibling. You don't fight over who the sibling is, right? I'm the sibling. No, I'm the sibling. Stupid, I was born first. You're the sibling. They are each other's siblings. Only one of them gets the -1 notation, though. How do we find an inverse? What did I tell you up here? What was the magical step for finding the inverse? Switch x and y. That's all you have to do for these ordered pairs. So let's go ahead and list it. On right here, we'll say f inverse of x, and the way you do that is you put a colon there, and I'm going to list them in braces. This should technically be in braces up here. I didn't make these notes. They should technically be in braces to show that it's a set of numbers. All right, so this is going to make sense to you. Watch this. If my original function in the first ordered pair takes a -2 and changes it into a 4, or you could use the word maps as well, it takes a -2 and it maps it into a 4, what is my inverse going to do with the 4? It's going to take the 4 and turn it back into a what? A -2. So all we're doing is we're interchanging the x and y. Look at the next ordered pair. If my original function took the -1 and turned it into a 2, what is my inverse going to do with the 2? Turn it into a -1. You got the idea? All right, so what's going to happen to 0, 0 when I switch the x and y? It becomes 0, 0. Right, yeah, it stays the same. What about the point 1, 2? It becomes what? 2, 1. And what about the point 2, 4? 4 comma 2. Yeah, yeah. This is the inverse. This is the inverse. Now, I got to check. Here's what I got to do. Notice I'm calling it a function right here. I'm calling it a function. I better check. I better check to make sure it's a function. Now that I've created a brand new function, let's see if it itself is a function. How do I check to see if any function is actually a function? I check to see if the x's repeat. Do any x's repeat? Oh boy. Now I've got a 2 going to a negative 1 and a 2 going to a positive 1. That is no bueno. So I need to restrict, it says down here, I need to restrict the domain of f if necessary so that the inverse function is truly a function. Okay? Now, how do I restrict the domain? I have to go back up to the original. Who are the two culprits? Well, this one guy here. The negative 1 mapped to a 2, and the 1 also mapped to a 2. So the 2 is 2 times the negative 1 and 1. You can decide if it's a set of ordered pairs, which one to keep and which one to get rid of. It's up to you. I need to restrict the domain, so I need to get rid of one of those. Which one do you want to get rid of? Let's get rid of the negative one. Try to reduce negativity in your life. So I'm going to restrict the domain by crossing that out, which means now I'm going to cross out this ordered pair right there. So it's no longer in the set. Okay? So when I restrict the original domain, here's what I say. I say x cannot equal what x value in the original one? X can't equal negative 1. That's how we restrict the domain. Don't use negative 1 as an input. Okay? We can use positive 1 still. It goes to 2, but now there's no double repeated. Okay? Now, here's why the horizontal line test. If the inverse function has to have no repeated x values, couldn't we check that on the original function without switching it first if it was 1 to 1? Yeah. So for a 1 to 1 function, you can't have any repeated x values, nor can you have any repeated what? Y values. So I could have told right away, I could have easily seen right away, I have a 4, a 2, a 0, and a 2, and a 4. Uh-oh. Do I need to restrict the domain some more? Yeah, I not only have a repeated 2, I also have a repeated 4. So if you notice, I have 4 going to 2 places. You can check if a function is going to have an inverse function before you even flip them around just by checking the y values. That's the horizontal line test. So which of those do you want to get rid of? The negative again? All right, let's get rid of this one. So the negative 2, 4 is out, which means the 4, negative 2 is out, which means I need to change my restriction. X can't be negative 1 on the original function, nor can it equal what? Negative 2. There you go. Now let's check because I didn't see the first one, the repeated 4 at first. Do I now have a function in the original function? Let's check. Do I have any repeated x values? 0, 1, and 2. Do any of those repeat? No. So it's a function. Let's check the y values for 1 to 1-ness. Do I have any repeated y value now? 0, 2, 4? Those are all unique as well. So I know right away now that the inverse will end up being a function. There's only one way to code and only one way to decode. Got it? We're coding messages here. Okay. That's not so bad. That's not so bad.
So we get to choose which one we get rid of.
When it's ordered pairs, you get to choose. Yeah, when it's ordered pairs, you get to choose. Like up here, let's look at the x squared up here. You see how I restricted the domain up here to x is greater than or equal to 0? I could easily have done this. I could have said, you know what? I'm a negative person. I'm going to restrict the domain to x is less than or equal to 0. And all of my friends know now that they only use negative values. So if I send them a 25, they know it came from a what? A negative 5 instead of a 5. I could have done that. But most people are not evil like that. Most people tend to focus on the what? Hopefully. The positive. And so we would restrict that to x is greater than or equal to 0. But to answer your question, it works just as nicely if you choose x is less than or 0. The key is we have to make the numbers that are given have no repeated y values and no repeated x values. We have to make the graph that we're given pass the horizontal line test. So we have to get rid of one of the branches that makes the horizontal line test fail. Okay? All right. Let's go to the next example here. We already talked about x squared. You see how x squared fails the horizontal line test? It's not a good coder. So what can we do to make it one-to-one? Well, as I said up above, we can take the domain and we can restrict it. I'll use green here. I can restrict the domain of y equals x squared to all values that are greater than or equal to 0. If I do that, what I'm doing is I'm looking at this branch right here. I'll highlight it. I'm looking at that branch there. And if you want, you can even do this. You can scribble this one out. Now let's think about graphically what's happening here. Graphically what's happening here. Okay? If I were to want to generate the graph of an inverse function, how would I go about finding the graph of an inverse function? Well, it turns out that to generate the graph of an inverse function, all you got to do is reflect your original function across the magical mirror, the line that is y equals x. Y equals x is your 45-degree line that passes through the origin. If you reflect your original function across that magical mirror, you'll get the graph of the inverse. Now, you can also do it ordered pair by ordered pair. Watch, I'll show you. Let's look at the graph of x squared, the highlighted branch, and let's just look at a few ordered pairs and see if we can switch them and to graph the inverse. So let's start at the origin. That's 0, 0. If I switch 0, 0 around, what do I get? I get 0, 0. So that's going to be the same point on the inverse function, right? What about right here at 1, 1? What happens if I switch 1, 1? I get the same point, right? So that point is also going to be on the inverse. Let's look at this point over here in green. This one's actually different. This is the point 2, 4. If I switch that around, what am I going to get? I get the point 4, 2, which is over here. See that? Now we're getting somewhere. And I can keep doing that. So if you turn your head at a 45-degree angle, I always thought this would make a good yearbook photo. Turn your head at a 45-degree angle so that you're staring at the line y equals x running straight down the middle of your nose. Now imagine folding the graph along that red line. Would the highlighted green part and the blue part line up with each other if you folded it along that line? They would. They would. Okay? Now notice what happens. If I only reflect the highlighted part, I get the solid blue line graph. Does the solid blue line graph pass the vertical line test? Yes, it does. If I were to reflect the entire parabola, let's uncross out the left part of the parabola. If I did not restrict the domain to greater than or equal to 0, what would that branch over here, let's highlight it in blue. What would this blue piece over here look like if I reflected across the line y equals x? It would look like this dotted line piece over here. Again, if you want to verify it, turn your head at a 45, fold those two pieces on top of each other, and you see that they're going to coincide. So if I reflected the whole parabola in green, I would get this entire sideways looking parabola. That entire sideways looking parabola. Does that pass the vertical line test, the result? No, the result would fail the vertical line test. See that? So I would know right away, oh, that's not good. That's not good. That's not a good way to code a message because my inverse fails the vertical line test. Well, guess what? If I keep that vertical line on and I reflect it across, that vertical line reflects across and becomes a guess what? A horizontal line. The vertical line, if you reflect it across the line y equals x, becomes a horizontal line. So here's how you could tell right away that x squared was not one-to-one. It passes the vertical line test, right? X squared passes the vertical line test, but does it pass the horizontal line test? Nope. Every single y value other than 0 comes from two different x's. Okay, so that's how we know it doesn't work. So again, we would restrict it, and most people choose positive. We would only look at non-negative pieces. So we do want to include 0. X can be greater than or equal to 0. And when I do that, I do not get the entire blue graph. I get the part of the blue graph that's not dotted. Okay? Now, what do we call that function that is the inverse of x squared? How did we say earlier you unsquare a number? You square root it. You square root it. Okay? The other version down there that we're not going to use would be the reflection of the positive part across the x-axis. We're not using it. So this is your new parent function. We call this the radical function or the square root function. The square root function. And it becomes a new parent function. The square root function. What does the square root function look like? If we were to, let's graph it over here. If I just look at y equals the square root of x, here's what you're going to graph it as. You're going to draw an x and y axis, and then you're going to come in here, and you're going to come from the origin, and you're going to draw it up and going out like that. That's your parent square root function. It passes the vertical line test. What's the domain of this parent function? 0 to infinity. So let's use interval notation. X epsilon, 0 to infinity. There's the domain. What's the range of this function? What y values does it take on? Also 0 to infinity. Yep. Yep, there you go. So the square root function is only half of the parabola that fell over. Half of the parabola. Okay, and by convention, we chose the positive half instead of the negative half because by nature, we try to be what? Positive. Okay, we try to stay positive. All right, there's your parent square root function. Now, we could do the same thing with x cubed. How would you uncube a number? If unsquaring a number is taking the square root, how would you uncube a number? Cubed root. That's what we call it. This is the cubed root function. So this is a new parent function right here, the cubed root function. Okay, that's your parent cubed root function. Now let's see what this graph looks like. To get the graph of the cube root function, we're going to take the graph of x cubed. Now it is graphed off to the right, but it gives away too much. Let's look at the graph of x cubed. We already know what x cubed looks like. It comes in like this, and then it leaves like that. There's the graph of x cubed right there. First of all, is x cubed a function by itself? Does it pass the vertical line test? It does. Is it going to have an inverse that is automatically a function, or are we going to have to restrict its domain to make it so? How can we tell if it's going to automatically have a function that's an invert, or an inverse that's a function? We have to check to see if it's what? 1-to-1. Every 1-to-1 function will have an inverse that's automatically an inverse. There's only one way to code it and only one way to decode it. How can we tell graphically? It has to pass both the what? Vertical and the, I crossed it out, it's right here. The vertical and the horizontal line test, yeah. Does this graph of x cubed pass the horizontal line test as well? It does. It passes the horizontal line test. So x cubed is already 1-to-1, isn't it? Without any restrictions. Without any restrictions. We don't have to say, let's only look for x greater than or equal to 0. It's going to have a function that's an inverse that's already a function. Now, what is it going to look like? To show that, I'll come over here to this graph. The red graph is x cubed, and if we reflect the red graph magically across the line y equals x, turn your head at a 45, and then fold it along that line. Does the blue graph coincide with the red graph? It sure does. It sure does. Now, here's what the x cubed graph looks like. Let's graph it by itself. I'm going to look at y equals x, or the cube root, sorry. Y equals the cube root of x. Here's what it looks like. This is going to be a new parent function. All right, notice it kind of looks like x cubed, but here's what you need to know the difference between them is. They're both monotonic increasing. X cubed comes in, how do I get to different color? Oh, there it is. I'm trying to get to red. That'll work. X cubed comes in curving downward. You see that? It comes in curving downward, concave down. We say concave down. But what does the cube root of x come in as? It comes in curving upward. It's curving upward. Whereas the graph of x cubed is curving downward. Now here's the other important feature. X cubed gets horizontal right there at the origin. It gets horizontal. It actually flattens out to a singularity that's flat, perfectly flat. What does that mean about its inverse then, right there at the origin? The cube root of x gets what? Gets vertical. Yeah, if you're a skateboarder, you're in good business right there because you're going to hit vert at a single point. All right, so when we draw the parent function without the x cubed there, here's what we're going to do. I'll zoom out so you can see it gets vertical. So you're going to come in curving upward, and as you approach the origin, you're going to go vertical like that. And then you're going to come out vertical and go off like that. This function is actually an odd function. It has origin symmetry. It has rotational symmetry. Both of them have rotational symmetry. They're odd functions. Okay. There's what the graph of x cubed looks like. What's the domain of x cubed? Or the cube root of x. Sorry, I keep saying x cubed. What's the domain of the cube root of x? The cube root function. Negative infinity to infinity. Yeah, so you could say it x epsilon, negative infinity to infinity. Or what's another way to say that? All real numbers. Yeah. What would be the range of the cube root function? Also all real numbers. Yeah. And then the only thing I want to say about this other than domain and range is that it's an odd function. It's an odd function, which means it has origin symmetry. The cube root of x did not have any symmetry. It didn't have rotational symmetry or origin symmetry because we had to restrict the domain. All right, so there it is. You have two new functions today that you're going to add to your catalog of parent functions. The square root function, which is just a single branch sticking out from the origin. And then you got the cube root function, which notice in quadrant one, doesn't the cube root function kind of look like the square root function in quadrant one? Yeah, it kind of looks the same. The only difference is it has a partner down there in quadrant three that comes in and goes vertical. Okay, whoo, got it? All right, let's look at example 2. Graph the function f of x and determine if the domain needs to be restricted to make it one-to-one. Then algebraically find the inverse and sketch its graph. Okay, the starting function is 1/3 x squared. Just knowing what we know about what this graph is going to look like from our past experience with all x squared graphs, you think it's going to be one-to-one to begin with? No x squared graph will ever be one-to-one to begin with. They're all smiles, and the smile fails the horizontal line test, unfortunately. Let's go ahead and sketch the graph real quick. What is the 1/3 going to do to the graph of x squared? Vertically compress it by a factor of what? 3. That's just going to make it wider. I'm not going to draw x squared and 1/3 x squared. I'm just going to draw 1/3 x squared like this. I'm just going to draw a little bit wider than a normal parabola. There's what the graph of f of x looks like. It fails the horizontal line test. You can see right here, boom. Okay, there's a point there, point there. It fails the horizontal HLT. Are you okay with the HLT, the horizontal line test? It fails the HLT. So we need to restrict the domain, don't we? What values of x do you want to restrict it to? Could I restrict it from 1 to infinity? Could I just look at these values? Would that be 1-to-1?
Yeah.
It would be. But why am I leaving out the pieces before that? What we want to do is we want to have the domain be as large as possible still. So instead of restricting it from 1 to infinity, what would be a better value to restrict it starting from? 0. Let's start at 0, and then we'll use the rest of the graph. Let's highlight. I didn't like crossing it out. Let's highlight that portion. Let's use all of those values from 0 to infinity, just like we did before. We'll restrict the domain from x being greater than or equal to infinity. And then what can we say about the other branch that we're choosing not to use? That we can kind of cross out if we want. So we're looking at half the parabola. Okay, so let's go ahead and write the restricted domain over here. We're just going to say x is greater than or equal to 0. If you want to put it in domain, let's put it in domain form. Okay, we'll say that the domain of f is now going to be restricted to the set of all x such that x is greater than or equal to 0. All right, now how do we find the equation of the inverse function? What was the very first thing I told you we do if we have the equation? We could reflect the graph across the line y equals x and see what it looks like. But remember how we did it way up here in the beginning. To find an inverse function, you switch x and y and then do what? Resolve for y. Yeah. So let's come down here. My function doesn't even have a y in it, does it? So I'm going to come down here. I'm going to take f of x equals 1/3 x cubed, or x squared. And my first step actually is to replace f of x with just y. That's kind of priming the pump a little bit. It's easier to work with x and y than f of x, because f of x is just this big, cumbersome, multi-symbolic thing that just means y, doesn't it? All right. So what's the money step? I'm going to use green here. What's the money step for all inverses? What do we do with x and y? Switch them. So I get x equals 1/3 y squared. Yeah. And now all I got to do is resolve for y. It's easy. This is algebra now. This falls back on your algebraic skills. What would you do first to solve for y? Would you take the square root of both sides right away? No, because you got a 1/3 blocking the y squared. So how do you get rid of the 1/3? Multiply both sides by the reciprocal of 1/3, which is what? 3. Multiply both sides by 3, and we get 3x equals y squared. Now what? Now can I take the square root? Yeah, so I take the square root and I get plus or minus the square root of 3x. Now here's where it differs. Do I want both the plus and the minus? No. The plus is going to give me the top portion. That's the plus. The negative is going to give me the reflection across the negative. I don't want the negative portion, do I? Okay, because I restricted the domain, so I'm only going to get the positive version. So we're now going to say y inverse equals positive square root of 3x, which, if we fancy that up now, what's another name for y inverse? Since we started with f, we'll use what? F inverse. Yeah, it's just changing the name. Y inverse is the same as F inverse. And do I really need to put the plus sign in front of the radical? I don't. It's implied to be positive. So there it is. That's the answer for the inverse function. F inverse of x is the square root of 3 times x under the radical. Got it? Not so bad. We got 4 minutes, 3.5 minutes. You want to try and do B or save B for tomorrow? Let's save it for tomorrow. Now that we have the outline of what an inverse function is and we know what we're doing, we should be able to move through these last examples tomorrow much more quickly, okay? Because you've got a lot of theory, you got a lot of explaining happening today, and then you got one little example to kind of lock it in. So whatever time's left tomorrow after we finish, you'll have to work on the worksheet, okay? You probably have enough information now if you want to work on your worksheet and get a lot of it done. You just haven't seen enough examples in class to maybe see all the different varieties that you'll come across. But the idea is the same. You have the idea and plan it in your head. All right, so we will finish tomorrow. Any questions on today? An inverse function does what to the original function? What's the magic word? Undoes. There you go. It undoes it. An inverse function decodes, right? A function codes and then an inverse function decodes it. And we want it to be that there's only one way to code and only one way to decode. What do we call those functions, real quickly, where there's only one way to code and one way to decode? One-to-one. They are faithfully monogamous, like Minnie and Mickey. They're Minnie Mouse and Mickey Mouse, right? Faithfully monogamous one-to-one couples. Okay, we're done for the day.